Hello everyone, in this video I'm gonna solve question number 8 and 9 from problem set number 3, and I'm gonna solve a previous midterm question. So that's a very important video. So in question 8 we have a 280 turn coil is wound on the center leg of the sheet steel core given the relative permeability shown in the figure. A flux of 1 milliweber is required in the air gap. The core is built up to a thickness of 3 cm. Determine the coil current. In order to solve this problem, we need to draw first the equivalent circuit. So the equivalent circuit of this magnetic circuit will be, first, we have a coil, so we have a source in the middle. Then we have a reluctance for this air gap. Then we have two parallel reluctances, one for the right leg and one for the left leg. So this is the equivalent circuit. We have a flux, we have a source, and we have the reluctance for the air gap, and of course the reluctance of the core in the center, of course, and one reluctance for the right leg and one for the left leg. The area, the cross-section area, which is perpendicular to the flux, is constant through the circuit, which is equal to this width 4 times the thickness, which is given 3 cm. So the area is constant for all these reluctances. So let's start with the reluctance of the center. We have the length and we have the relative permeability and we have the area, so we can calculate the reluctance for the center. We can also calculate the reluctance for the right and the left side. In this specific problem, these two reluctances are constant, are similar, and equal to the mean length. The mean length here is given directly, 40, and the relative permeability and the area. The next step is to calculate the reluctance of the air gap. For the air gap, the relative permeability equal to 1, so we do not have relative permeability. The length here representing the length of the air gap. So we have 1 millimeter air gap, so this is the length for this reluctance. And we can calculate the reluctance of the air gap. Okay. Why we did all of these calculations? It's required to calculate the coil current. In order to calculate the coil current, the only equation that we know that can calculate the coil current is the magnetomotive force. If we can calculate the magnetomotive force, we can calculate the coil current, because the magnetomotive force is equal to N, which is the number of turns, times the current. We have N, and we can determine the coil current if we know the magnetomotive force. So the next step is to simplify this circuit to just a source and equivalent reluctance. This equivalent reluctance will be equal to these two reluctances in parallel, so the right leg reluctance and the left leg reluctance in parallel, then these two reluctances in series. So the right leg parallel with the left leg plus the air gap reluctance plus the center reluctance. After that, the magnetomotive force is equal to the flux times the equivalent reluctance. And we know this flux is given. So we can calculate the magnetomotive force and divide this magnetomotive force over the number of turns in order to calculate the current. For question 9, we have a ferromagnetic core with a relative permeability of 2000, is shown in this figure below. The dimensions are given, the depth of the core is given, the air gaps of the left and right sides of the core are given. If there are 300 turns in the coil wrapped around the center leg of the core, and if the current in the coil is 1 amp, what is the flux in each of the left, center, and right legs of the core, and what is the flux density in each air gap? So we'll start by drawing the equivalent circuit. We have a coil here in the center leg. So we have source and we have a reluctance for the center and reluctance for the right core and reluctance for the right air gap. Also, we have a reluctance for the left core and reluctance for the left air gap. So here is the equivalent circuit. Source, reluctance for center, reluctance for the right core, reluctance for the left core, reluctance for the right air gap, and reluctance for the left air gap. The question, is the area here constant or not? So we have the width of each core is equal to 7 centimeters and the depth is given as 7 centimeters. So it seems like the area is constant through all the circuit. But this is a specific case. It might be different from leg to the other. So we have area constant and we can calculate the mean right length and the mean left length, and they are equal neglecting the length of the air gap. If you consider the length of the air gap, they will not be equal. And because the length of the air gap is very small compared to the length of the core, we can neglect the length of the air gap in this question. So the length for the left will be 37, which is the mean length from this point to this point, multiplied times 3 to calculate the mean length for the left core and also for the right core. The length of the center from this point to this point, which is also equal to 37 centimeters. So we have all the data now given, and we can start calculating the reluctance. The reluctance of the center is equal to the length of the center over mu naught times mu r, which is given, times the area, which is calculated. Remember to convert all your given to meter. For the left core and right core, they are equal, again neglecting the length of the air gap, and could be easily calculating using the length of the right and left core and the area. And we have also the left air gap, which is not equal to the right air gap because the length of the air gaps are different. So we can calculate these two reluctance for the air gaps. The relative permeability for these two air gaps are equal to 1, and the length is given. Now we calculated all the reluctance. The next step is to calculate the equivalent reluctance. So we have these two in series and these two in series, then the equivalent of these two and the equivalent of these two in parallel, then in series with the center reluctance. So we have the center reluctance plus these two in series for the right core and the right air gap, representing this leg, and the left core and the left air gap, representing this leg. These two in parallel and in series with the center to calculate the equivalent reluctance. Now we have the equivalent reluctance, and we know the magnetomotive force. We can calculate the flux. So the flux is equal to the magnetomotive force, which is equal to the number of turns times the current, over the equivalent reluctance. Now, in order to calculate the left flux and the right flux, we can use the current divider rule. So the left flux is equal to the total flux times these two together over the summation of these two along with these two. So by using the current divider rule, we can calculate the flux in the left and the flux of the right, of course, or we can subtract the flux calculated from the total flux to calculate the flux on the right side. The last thing is to calculate the flux density in the two air gaps. So we have the right air gap and the left air gap. Flux density is equal to the flux over the area. We have the flux in the right air gap calculated in this part, and we have the area of this air gap. So we can calculate the flux on the right air gap. For the left air gap, we have to use the flux left air gap and the area for the left air gap. Here, these two areas are equal, but they might be different. Okay, now we finished all the questions from the problem set, and here we have example from previous midterm question. Okay, so here we have a previous midterm question. This question is designed by Professor Nassar, and this is a level for the midterm question in the magnetic circuits. Okay, let's start. Consider the magnetic circuit shown in figure 2, which is this figure. The coil has 500 turns and supplied with current equal to 2 amp. The thickness of the core is 8 centimeter, so we have the core thickness equal to 8 centimeter, representing this depth. And the air gaps have 0.3 centimeter and 0.6 centimeter lengths, so the lengths of the air gaps are given. The leakage flux and fringe effect can be neglected. If the relative permeability of the core is 4000, find first, sketch the equivalent circuit, then calculate the magnetic flux values in the middle, left and right legs, then calculate the magnetic flux density in air gap number 1, which is this air gap. After that, if the fringing effect were included in the calculations, would it lead to a larger or smaller magnetic flux in the air gap? Justify. And of course, you don't have to do any calculation to answer this question. The last part, if both air gaps were not present, would this need a larger or smaller current to produce the same flux in the middle leg? Again, you do not have to do any calculation to answer this question. Okay. First, we need to sketch the equivalent circuit. We have a coil, so we have a source. We have this core in the middle, so we have a reluctance for the middle. We have air gap in the middle, so we have this reluctance representing the air gap in the middle. And we have a left core, so we have a left reluctance. And we have a right core, we have a right reluctance. And we have an air gap in the right core, so we have this reluctance representing this air gap. Of course, we have flux for the middle, flux for the right, and flux for the left. So this is the equivalent circuit of this magnetic circuit. Part B, calculate the magnetic flux values in the middle, left, and right legs. Again, in order to do that, we need first to calculate all the reluctances given in the circuit. So we have the reluctance for the left side. We need to calculate the mean length for the left core and the area, which is constant for this left leg and this right leg. However, it is not constant for the middle core because the width here is 6 centimeter, not 5 centimeter, and this is one of the tracks. So the area here is not constant. Take care. So we can calculate that the length of the mean length for the left core and for the right core, and for the length for the right air gap is given, also for the middle air gap and the middle core. And as you see here, we have 6 times 8, not 5 times 8 as in these reluctances. Okay, it's very important. Now, after calculating all these reluctances, we can simplify the circuit and calculate the equivalent reluctance. So the equivalent reluctance here, we have these two reluctances in series parallel with the left reluctance, then series with these two reluctances. Okay, after that we can calculate the middle flux, which is the magnetomotive force in this coil over the equivalent reluctance. After that, as we did in the previous question, we can use the current divider rule to calculate the left flux and the right flux. So this is for part II. For part III, the magnetic flux density in air gap 1, which is this air gap, is equal to the flux in this air gap passing this air gap over the area of this air gap, the area perpendicular to the flux. Okay, it's very important. Now to the next part. If the fringing effect were included, would it lead to larger or smaller magnetic flux? Okay, if we include the fringing, this will lead to more area in the air gap. And if the area is larger, this means that this reluctance will be less. So this reluctance will decrease. And if the reluctance is decreased, the flux will increase. So it will lead to more flux. For part V, if both air gaps were not present, would this need a larger or smaller current to produce the same flux? Now, if we do not have these two air gaps, the equivalent reluctance will be much less. If the reluctance is less and this flux is constant, so it will need to smaller current to produce the same flux. Okay, this question is part VI and VII for the same question. So we have here, in order to reduce the core losses, the magnetic core is typically laminated. Based on your understanding of magnetic circuit principles, answer the following questions. First, mention the different types of losses expected in the core and how each type is affected by laminating the core. Part VII, show in figure 1 how the core is laminated and explain briefly why you choose the direction of the lamination in your answer. So for this part, we have two types of losses, eddy losses and hysteresis losses. And by laminating the core, we are reducing the eddy current, but the hysteresis current will be the same. For part VII, this is the direction of the lamination, and it's chosen like this for manufacturing reasons, as will be explained in the lecture. Okay, now this is all I have for this tutorial. Thank you and see you next week.